In the context of the autonomous vehicle, we need a variety of sensors to detect the complete environment and navigate the car safely. Different types of sensors have proven to be useful, and together they complement each other optimally. So in today's coffee break, I'll briefly introduce you to the concept of a LiDAR sensor, its output, and also the algorithms which turn a bunch of points into an understanding of the autonomous vehicle's environment. The second part deals with how we can test these algorithms with physics-based sensor simulation by creating synthetic point clouds along with ground truth information. This also enables you to work with simulation in a continuous integration environment. So, what is a LiDAR sensor? While there are plenty of variations around, I'd like to keep it simple for now. The sensor emits near-infrared light waves into the environment, which is reflected by its surrounding objects and returned to the sensor's detector. The time a pulse takes to return is used to calculate the traveled distance, and additionally, based on the number of reflected photons, the reflectivity of the hit object is calculated. The resulting group of points is also called a point cloud. Now that we know what the LiDAR sensor is and that it creates a 3D point cloud of its environment, we can dive into perception algorithms which take this data as an input. A use case is the recognition of objects. For this purpose, the points of the point cloud are clustered and checked for various features to assign several points to a vehicle or a pedestrian, for example. The detected objects, of course, should be bypassed by the autonomous vehicle. However, to get an even better understanding of the environment, the point cloud is used for mapping and localization. This process is called simultaneous localization and mapping, or SLAM in short. Contrary to object detection, this process detects where our vehicle may move. On one hand, these algorithms must be designed and implemented. On the other hand, they also must be tested. A test can be done, for example, by recording a real test drive with a real sensor. The quality of the sensor data is of course excellent, but the test drive is expensive and it is difficult to produce corner cases. In addition, ground truth information must be provided for each and every frame to make automatic tests possible. But what is ground truth information in a LiDAR sensor? So, in addition to the existing information such as distance and reflectivity, an object category is added to each point of the point cloud. This indicates what kind of object it is. For real measurement runs, this can be created by our Understand AI annotator. Within the simulation, we get this information for free. To dig deeper into the testing use case, I would like to introduce you to the company XYZ. XYZ is a 3D vision company located in Paris, with their mission to bring you real-time 3D LiDAR processing. Their solution includes the previously mentioned algorithms for object detection and also for SLAM. And additionally, these algorithms also work sensor agnostic. To test their algorithms, we are using our physics-based sensor simulation, Aurelion, to calculate a 3D point cloud in a virtual environment. Here you can see our BlueEgo vehicle driving in a suburb scenario. The points across the environment are produced by a virtual LiDAR sensor with a 360-degree field of view, which is mounted on the top of the car. Now, we inject this information into LiDAR perception algorithms to detect objects and create a map of our environment. As time goes on, you can see that the information density is increasing, so the map gets better, and the detected objects are depicted with different colors. I think that this is already a great benefit, where ideas for improvement potentials can already arise by looking at it. However, to automatically measure the performance of your algorithm as part of continuous integration and to check whether the algorithm has improved or even become worse, the output must be automatically compared with ground truth information. For this, we are comparing the calculated class IDs of the perception algorithm with the ground truth information and are using the F1 and Jacquard score as KPIs to check how well the algorithm performs. We are doing this inside the tool RTMaps since it is comfortable to obtain the synthetic sensor data from Aurelion, and since XYZ is also providing their algorithms wrapped in easy-to-use RTMaps components. Back to the automatic test, and please note that the following is very important to understand. At the top left, you can see a visualization of a ground truth point cloud. This shows how the algorithm would perform if 100% of the points are classified correctly. At the bottom left, we can see how the algorithm performs on the point cloud without any ground truth information. We can already see that our white ego vehicle in the middle has a great understanding of everything close to itself and also the road. To get an even better understanding of how well it performs, we are plotting the evaluation of the F1 score and Jacquard score KPIs as a micro average, where a number of 1 stands for 100% overlap. In summary, a LiDAR sensor produces a point cloud that generates an understanding of the environment through various algorithms, such as object detection and SLAM. In the context of autonomous driving, these algorithms must be tested under a wide variety of conditions. To show the test workflow, we saw algorithms from the company XYZ and injected synthetic point clouds from our physics-based sensor simulation tool, Aurelion. To test them automatically, we use ground truth information, which assigns an object ID to each point within the point cloud. The ratio between true and false detected points can be expressed by different KPIs. Reach out if you're interested in reducing costs and improving your test with synthetic data.